Longest increasing subsequence. Given an integer array nums, return the length of the longest strictly increasing subsequence. So this is like a super classic DP problem, or it could be not a DP problem with even better time complexity. And maybe I'll show you that way and I'll show you the DP way for this problem, both in this video. I think this pattern is very useful. It's probably one of the first patterns I learned for DP problems. And it's like one of the only DP type problems that I can do bottom up instead of top down. Mostly I do top down DP. All right, so here's my nums. And they say the answer for this is 4. So the DP for this is like an n squared time complexity. And I think it starts out by, let's say we'll create the DP array. First, let me put some indices over these numbers. So each number has the indice above it. And then we'll create a DP thing. And we'll initialize everything in the DP array to like 1. All right, so this DP thing is saying, what is the longest increasing subsequence that ends at that index, at that particular index? So we initialize everything to 1 because each number can just be itself in the subsequence. All right, so we're gonna do like a nested for loop, an n squared for loop, where we say for I, blah, 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 and then for j equal I plus 1. So we start j at 1 more than I. And what we're doing here is we're comparing j to the value of I. So we do the n squared traversal, and we're gonna check if nums j is greater than nums I. So if this is true, then we can update dpj to be dp I plus 1, or if dpj is already bigger, then we just leave it. So for 9 is not greater than 10, so we don't really need to do anything there. And then we look at 2 is also smaller than 10, we don't have to do anything there. 5, same thing, nothing interesting until we hit index 6. At index 6, 101 is greater than 10. So that means we can build a subsequence going from index 0 to index 6, and that should be whatever at index I plus 1. So we update this to 2. That means the longest increasing subsequence that we can build that ends at index 6 is length 2. And it's like 10, 101, basically, so far for the numbers that we've calculated. We take j all the way to the end. 18 is greater than 10, so we also update this one to 2. And then we increment I, and then we pull j back to I plus 1. So we do the same things again, and we just keep doing that for the whole thing. 101, it's greater. So then it's like 1 plus 1 is already 2. So we don't actually update anything there. Same thing for the 18. We don't actually update anything there. And we increment our I, and we do it again, man. We keep going. Now here is, maybe we're gonna see some more interesting things happen. 3 is less than 5, we don't do anything. 7 is greater than 5. So we're gonna update the index here to be dpi, which is 2, plus 1. Because the longest index ending at 5, or the longest length, is already 2. And then we found one more that's longer, so we can just tack on one more number to it. So we update this to 2 plus 1, which is 3. And we keep going. "101 is greater than 7, so we can update dpj to be dpi plus 1, which is 4. And the same thing here, 18 is greater than 7, so the longest increasing subsequence ending at index j is 4. And then that's it. Can do it one more. 18 is not greater than 101, so we don't have to update anything. And then we just keep track of the maximum number that we saw there, which is 4. So I'm gonna implement this in code now real quick. So first thing I like to do is create n for the number of elements in nums. And here's my double for loop. J equal I plus 1, j less than n, j plus plus, and then it's, I guess we have to create our dp array, so let's initialize a new vector, call it dp. It's going to be of size n, and we fill it with all ones initially. I guess we can say initialize our answer to 1, because as long as there's an element in nums, the answer will be 1. Based on the constraints, there will always at least be one element. So we got to check if nums j is strictly greater than nums I, then we can update dpj to be equal to the maximum value of itself, or dpi plus 1. And then we should remember like the best value that we've seen. We'll store that in the answer variable. And then that's it. That is it, man. I already submitted this before, so I know it should work. And that is the dynamic programming version of how to solve longest increasing subsequence. But there is a more efficient way. This way is acceptable, mostly, especially with the constraints here. But there's a faster way that involves binary search, and I'm about to show you how to do that one next. Alright, so another way we can solve this problem of the longest increasing subsequence is using binary search. This is like more optimal than the n squared dp solution, but it's a little bit tricky and it's not too hard to implement though. So I'll try and break it down for you. So like, I'll use example 2 here. So in this example, we're given these numbers 0, 1, 0, 3, 2, 3. And they want to know the longest increasing subsequence, which the answer is supposed to be 4. I'll put x's above them. That's like these numbers, they're always increasing, strictly increasing, and that's the longest we can get, 4. So let me put indices now. For the nlogn lis, we'll start with an empty vector or an empty array, and then we're gonna iterate through each index, and we're gonna do a binary search on lis to find the first number greater than or equal to the current number. And in C++, that's called a lower bound. I think in Python or something it's like bisect left or whatever. I don't really know Python, so I'll use C++ terminology. We're gonna do a lower bound on, this is our target 0 or the current index, and the lower bound, we're gonna do it on lis. So we say we want to find the first number greater than or equal to 0 in lis. There is none. So if there is no number greater than or equal to it, then we just append it to the vector or push it back. So now we have one number in our vector of longest increasing subsequence, and then we can move on to the next index. So we do a lower bound on lis. The first number greater than or equal to 1 is nothing. There's no number, so we append that as well. And we move on to the next number. The first number greater than or equal to 0 is 0, but since it's already in there, we don't do anything. We just skip over it. Continue to the next one. And you might be wondering, like, maybe why don't I try to use an upper bound or find the first number that's greater than 0? It's because this problem statement says it's looking for a strictly increasing subsequence. So if it said something like greater than or equal to subsequence, then maybe we could use upper bound or just find the first number greater than it. For the number 3, we're looking for the first number greater than or equal to 3. There is none, so we push it back to the vector and then we can move on. 2, first number greater than or equal to 2. It's 3. So what do we do in this case? We simply just replace that number with this, because having 2 there is going to be strictly better than having 3 there, because it will allow us to build an even longer subarray or subsequence with like future numbers, I guess. And then we keep on keeping on, man. So the next number is 3. The first number greater than or equal to 3 doesn't exist, so we just push that back. And that's like the main idea behind this binary search nlogn longest increasing subsequence. Now let me try to code it up. So n is the number of elements in nums. I'm going to create my lis vector that's initially empty. I'm going to iterate over all of the elements in nums, and then I'll do a binary search. But I'm not going to implement my own binary search. I'm just going to use the standard library because it's already there and it's nice and powerful. So I'll say, find me the first number greater than or equal to, which is a lower bound in C++. And we want to scan the whole, well, not nums. We want to scan lis, the entire vector. And our target that we're looking for is going to be the current number, nums I. So that's it means iterator. So this lower bound returns the first iterator. And we can say if that iterator is equal to the end, this means no number exists that is greater than or equal to nums I. That's what this means. So in that case, we'll just append or push back nums I. Otherwise, if it's not lis.n, that means they have found something. Like the binary search, the lower bound did find a value, and we just have to make sure that that value is greater than nums I, and then we'll just replace it with nums I. And then at the end, we just want to return the length of the lis, because that's all it's asking for. Return the length. And hopefully I coded that up cleanly, and I can just hit submit and it should work. Easy work. That's all there is to it. Very powerful tool. You can use this technique in so many different problems. Maybe I'll make a little list of some problems where you can use it in. The vector lis, the longest increasing subsequence, doesn't actually contain the longest increasing subsequence, but it does contain the length, the possible length of a longest increasing subsequence. So that's just a little extra. Let me talk a little bit about what we just said with where BetSimp, trusted member in the community, has told us that the LIS doesn't actually contain the real subsequence because it can get out of order and it can get funky. So the LIS is only useful to know like how long a possible subsequence could be. So in this case here, let me show you this one. Let me erase all this junk first. So in a case like this, whenever we have our LIS and we're iterating through and we're doing the thing and we look for 1, nothing's there, we append it. We look for the 3, nothing's there, so we append it. We look for the 5, nothing's there, so we append the 5. Now we have an LIS 135. But then we get to the last index and we look for a 2, greater than or equal to 2. We find the 3, we replace the 3 with the 2, and now the LIS is all weird. So don't count on this technique to actually give you the LIS if you're looking for like literally the values in the LIS. This is only good for what the possible length could be. So like a subsequence 1, 2, 5 is not possible because 2 is the last element. So how are you gonna go from 1 to 2 and then back to 5? It ain't happening, man. So that's an important note. And thank you very much, BetSimp, for pointing that out. If you don't know BetSimp, man, what you doing out there?